So the topic of this CGR is Bootstrap method, trend and application in biomedical research. So basically, this Bootstrap method is first come in existence in 1979, and basically this method is used to know the sampling distribution of statistic and also to measure the various variability parameters in the statistics through this technique. So these are the contributors of this CGR. Now, Bootstrap technique, as per according to Dictionary of Statistics in the medical science, the Bootstrap is a database simulation method for statistical inference, which can be used to study the variability of estimated characteristic of the probability distribution of a set of observation and provide confidence interval for parameters in situations where these are difficult or impossible to derive in a usual way. In general, bootstrapping statistic is a form of hypothesis testing that involves resampling a single data set to create a multitude of simulated samples. These samples are used to calculate standard error, confidence interval, and hypothesis testing. This approach allows you to generate a more accurate sample from a smaller data set than the usual method. It is also an important parametric method for estimating and analyzing data, including hypothesis testing and standard error and confidence interval. As I said, the bootstrap procedure produces a variety of value whose variability reflects the standard error that would be obtained if sample were repeatedly taken from the sample population. The bootstrap make no distributional assumptions, may therefore be more appropriate for analyzing health data than the usual statistic method. Now the objective of this CGR is, the first objective is to estimation of statistical error and confidence interval using bootstrap method. The second one is the comparison of measures estimated through the bootstrap simulation and usual method. And the third one is the trends and practices of bootstrap method in original biomedical research articles. So, as we know that when we are doing a research, generally we never know about the population parameters. But we want to know about the population parameters, but this is a very difficult to measure the population parameters of the whole population due to various reasons. Either it due to the lack of time, money, human resource. So the general concept of the statistical inference is, we have a population of size, and that population may be any kind of disease, like it may be the prevalence of tuberculosis, it may be anemic patient, it may be the pregnant woman. So from that population, we are taking a small sample from this population through a statistical technique, and we are analyzing this sample and making inferences about the population. Here, suppose if we want to measure the this is the population mean versus sample mean, and suppose if we want to measure the hemoglobin level in the pregnant woman. The population is about the hemoglobin level of pregnant woman, and we have in a Lucknow district, if I say, so if we take the sample from this population and we will measure the mean of from this sample, and when we'll compare whether it is the sample mean is equal to the population mean or not. So generally, or you can say that probably it is not always possible that the sample mean is equal to the population means. So why this not come to the equal? It means during the process of during the process of sampling technique, we are committing some kind of errors, due to which we are not able to make this statement that population mean is equal to the sample mean. So what is actually the sampling process? The sampling process says that if we have a population, and from that population, if we are taking a sample of size n through the sample random sampling technique, and if we are doing repeatedly, taking repeatedly sample from the population, then the sampling distributions of the population, maybe we can find out the sampling distribution of the population. The theory suggests that if in this process, the sampling distributions which we got, the mean of this sampling distribution is equal to the population mean, and with standard error sigma by root n. Now, if we connect the previous example where we have taken the mean hemoglobin level of population and the sample, so we can relate through this formula the population parameters is equivalent to the sample statistics plus minus random sampling error, or which we can say the standard error. The standard error is basically defined by the variance component divided by root of under root sample mean component. So standard error formula are derived for the various statistics like mean, proportion, correlation, regression, odds ratio, etc. And we can use these formula directly to estimate a standard error. Some formula we have mentioned here. This is the standard error formula for mean and proportion. This is basically in the case of sample. In the case of population, at place of S it will be sigma, and in place of a small p it will be capital P, means population proportion. So these are the some formula which are already derived, and we can use this formula directly to estimate the standard error. Now the above formulas are derived under the assumptions that the sample are drawn through the simple random sampling techniques. The formula for a standard error like mean and proportion is also available for the other probability sampling technique such as stratified sampling, cluster sampling, systematic sampling, etc. Usually in the many hospital based study, the probability sampling is not possible, because we know that in the most of the time either we are taking the data from either the OPD or from the those patients, only those patients who are registered in the SGPGI. We are not actually we are taking sample as per their availability, not from the whole population. So there are various statistics like median, mode, quartile, etc. The standardized formula for standard error is not available even for the probability sampling techniques. Now the concern is how to measure the variability like standard error or confidence interval. For those, the formula are not available or not derived. So here basically Bootstrap is the techniques. By using these techniques, we can estimate the standard error and confidence interval of those statistics whose formula are not derived. So in the Bootstrap, I will explain through this pictorial method. So suppose we have a 2 bucket. In one bucket we have 5 ball, and the another bucket is empty. So what actually we are doing, we can pick a ball through a simple random sampling method, and we replicate this ball and then put the replicated ball in the empty bucket. So basically this process is known as the sampling with replacement method. Means we have pick one sample or data randomly and then put again it, means replicate it and then put in the empty bucket. Then again put another sample and then replicate it and again put in the another bucket. So by this way, by repeating this process again and again, we can generate a parallel sample of the same size. So now here in the other bucket, we have generated a parallel sample as per our original sample. So we can repeat this process again and again till how many samples we want to generate. Like we can generate 100, 200, 300. So like this way, we can repeat this process again and again, and we can generate various samples of the same size. This is the overall presentations of a summary of this and the bootstrapping. We have a sample of size n, and from this sample we have generated here 3 different samples by using the previous sample. Now here we have taken numerical examples. Suppose if we have a body fat in percentage of 10% whose age are between 25 and 30-year-old. So initially we have this data. So what actually we will do? First, we have checked the distribution of this data, and we found that the distribution is positively skewed. Now further we have analyzed its descriptive statistics, and we see that we got most of the descriptive statistics, but when we look on the 95% confidence interval and the standard error, we are not able to estimate the standard error and the confidence interval for median, standard deviation, interquartile range, and also the confidence interval for skewness and kurtosis. So how we can estimate this standard error and confidence interval? So here we can see that in the column 1 we have mentioned the sample number. In the column 2 is the original sample of size 10, and in the row we have mentioned the bootstrap sample drawn. So since we have 10 original sample, so from this 10 original sample we have generated various samples with the same method as I shown in the pictorial diagram. First we have picked one random number from these 10 and put in the as the serial number 1 here, and then again pick another sample and replicate it and put at the second place. So similarly we have generated the 10 sample from this data. likewise, we have generated here 200 samples. Now for each sample, we can estimate their mean, their median, interquartile range, standard error, or standard deviations. So now if we see these column, mean, median, mode, so we have got the 200 means. Now if we plot these 200 mean, we will get the sampling distribution of the mean. Here we have shown, here we have plotted the mean. In the first picture, we have taken the 200 times resample, and in the second picture, we have resample it 1000 times. So in the first picture, we can see that the distribution is looking some skewness. But in the second, after 1000 resample, it shows like the normally distributed sample distribution. Now, from this generated bootstrap statistics, we can estimate the standard error and confidence interval for the statistics, which we are not able to estimate through the usual method for like the median, standard deviation, or interquartile range. Now, this is the overall summary. As I said in the previous slide, the sampling process and the theory, what theory suggests. Now, in the lower, we can see the bootstrap process. As I said, we have a population, and from that population, we are taking a sample. And from that sample, we are making the resampling process to find out the sampling distribution of the data. Now we have illustrated this through the usual method versus the bootstrap method. The first example we have taken for the mean and its confidence interval. So suppose an investigator is interested to know, is there any difference between the usual confidence interval versus the bootstrap confidence interval on normal population data. So for this, to estimate this usual or normal confidence interval method, 5 random sample of size 80 children were drawn from a population, that is, we have taken here the National Family Health Survey 5. So basically, the data which we have of the National Family Health Survey, we have considered this data as a population, and from that population we have taken a small sample of size 80, and we done the analysis for the comparison of bootstrap method versus the usual method. Now, if we see the 95% confidence interval of this usual method versus the bootstrap method, we find that there is no difference when the population is normal. The usually differences we can see here, the first or second decimal places. So from this we conclude that the usual and bootstrap method will produce a similar result unless the data violate parametric assumptions. So if means what I want to say, if our population is normal and from that population we have taken a sample which is also normal, and if we take either we can estimate the confidence interval either through the usual method or through the bootstrap method, both will produce the similar result. Now, if you see the variability across sample, so to measure this variability, we have taken additional 15 sample. We draw the additional 15 sample so that it will become the total 20 sample of the same size 80, and then we have replicated this till the 5,000 times, and we see the variability of each sample, because we have replicated each sample till 5,000 times. And when we see the variability of across the sample, so we found that at means 95% times these samples are come, means the population means hold or comes between these sampling distribution, 95% confidence of the sampling distribution. We can see here the sample number 8. Sample number 8 is basically the mean birth weight of this sample does not contain the population mean. So if we take these samples, means if we draw this sample from the population, so this would misinterpret the population, although the population mean is very close to the lower bound of the confidence interval. Now what we conclude here is the bootstrapping cannot fix a small or biased sample. Data cleaning prior to bootstrap analysis can help if influences cases are the cause of the misestimation. This is the estimates from the populations from which we have taken these samples of size 80. So we can see here the mean, the sampling distribution of the population is almost normal, and the mean is around 2.8 kg of this birth weight of the children, and the other statistics. Now take another example of median and their confidence interval. In this example, uses a subsample of size 200 from the same population National Family Health Survey, which include maternal and child health information on approximately more than 6 million women. So the investigator is interested in estimating the median and the 95% confidence interval, usual versus the bootstrap, for two variables known to have skewed distribution. One is the out-of-pocket expenditure on delivery, and the another is hemoglobin level. Now, if we see the sampling distribution of these two variables after 5,000 times replication, in the case of out-of-pocket expenditure on delivery, we found that the sampling distribution is non-normal, and we can say that this is a asymmetric distributions. So the sample mean of out-of-expenditure is not very close to the average bootstrap median, suggesting that the sample estimate is a biased estimator. And in the case of hemoglobin, the median is very close to the average bootstrap median, which suggests that it is an unbiased estimate. So here in the first diagram, we can see the difference between the sample median and the bootstrap median. But in the case of hemoglobin, both median are very close. So, and the distribution seems it's converges towards the normal distribution. Now, if you look the confidence interval, of this usual versus bootstrap, we found that in this case, the bootstrap method is more accurately predicting the mean of the population. So here on the y-axis, we have taken the population median, is the red line showing the population median. In the second, in the case of hemoglobin level, where the sampling distribution converges towards the normal distribution, it shows that the both method, either we can take through the usual method or you can take through the bootstrap method, both are almost similar. There is no very much difference. Here is the overall comparison. Here we have population median is of the out-of-pocket expenditure is 3,500, and the sample median is comes 2,000, while the bootstrap median shows is 3,495 rupees, and their 95% confidence interval we have presented here. Similarly, in the hemoglobin, the population hemoglobin shows 7.2 and the sample is 7.15 and the bootstrap is 7.13. So what we conclude, in the case of skewed data, bootstrapping CI method may produce better result than the usual method, and if multiple methods are used, it may be useful to review and compare the estimate. If differences exist, it may be advisable to use the method that are most closely aligned with the estimates, population estimates, we can say. Now, we have taken another example. Here we have compared the two population mean. So for this, we have taken data of the systolic blood pressure and the place of residence of the 30 patients. So the investigator is interested to examine the difference of systolic blood pressure between urban and rural patient. So for this, we can see in the first table, the both the urban population out of 30, the urban is 14 and the rural patient is 16. The mean is 141.86 in the urban, and the rural mean of the systolic blood pressure is 120.56. When we analyze or do through the parametric methods, we use these tests to measure the difference between this rural and urban of the systolic blood pressure. We found that the parametric method suggests that there is a significant difference between the rural and urban. But when we measure this p-value through the bootstrap techniques, we found that the bootstrap p-value suggests that the p-value suggests that the mean difference is not significant among these two groups. Further, we analyze through their confidence interval. Through this confidence interval, we have measured the shape of the distribution. So we find that the shape of the distribution is coming minus 1.052, and for the bootstrap it is minus 1.100, which suggests that if the shape value of this shape is less than -1, this suggests that the data is negatively skewed. When we see or compare this sample result through the population here we see the population size is 21,407 when we analyze to see what is the actual situation in the population, we found that the population also suggests that these differences are not significant. Here the p-value is 0.055. So it means Bootstrap is suggesting the right things in the smaller samples. So if we concluded here, if the data is skewed, Bootstrap hypothesis test may give advantage over the conventional hypothesis test for testing of equality of means comparison. The shape estimated through the usual and Bootstrap method to measure the symmetry about the point estimate may help in understanding about the skewness of the data. Here results suggest data is skewed. So before applying the parametric method, its assumptions must be verified. Now another example, we have taken the correlation and the 95% confidence interval. So as we know that correlation are the standardized measure of associations, and there are formula to calculate confidence interval for correlation coefficient, but they are rarely reported. In this example, we illustrated the estimation of the confidence interval for correlation and highlighted the effect of sample size on the precision of the estimated confidence interval. So for this 5 random subsample of data ranging in size 50 to 1500 are taken to represent 5 samples of varying size that a researcher could take from the populations. And in the data, we have taken the child weight, child height, and the duration of breastfeeding from the same population. Now the correlation coefficient and Bootstrap confidence intervals are then estimated for each sample in order to demonstrate how sample size can impact the precision of an estimate and the use of confidence interval in interpreting this precision. Now here in this slide, the first one we have estimated through the usual method, and the second is estimated through the Bootstrap method. The child weight and child height, the data was the normal, but the distribution of breastfeeding was not normal. So accordingly, we have used the Pearson and Spearman rank correlation. So what actually we can see in the picture, when we have a smaller sample size, the correlation value is underestimated, means it is away from the population. Here in the y-axis, we have taken the population, this the dark line is showing the population R of correlation. So in the small sample, the correlation coefficient is more away from the population estimate. As we have increases the sample size, the confidence interval is become narrow. So we conclude here that the precision of the point estimate and confidence interval improve with increases in sample size. The confidence interval become narrow as the sample size increases. Thus, larger sample size will have the narrow confidence interval, while the smaller sample will have wider interval in both the method. This suggests that we have a better estimation of the true value of the correlation in the population when a larger sample size is used. The result of Bootstrap method suggests that we may get a better estimation of the correlation when the sample size is small and skewed as compared to the usual method. We can see here in the Bootstrap method, the correlation values is very, means it is much near to the population correlation as compared to the usual method. Now, what is the advantage of this bootstrap method? So bootstrap method does not rely on any parametric distributional assumptions. Bootstrap does not depend on a center limit theorem. It does not have complicated formula to memorize. All you need to know is the bootstrap principle. The bootstrap is a straightforward way to derive estimates of a standard error and confidence interval for complex estimators of the distribution, such as percentile points, proportion, odds ratio, and correlation coefficient, etc. Bootstrap is also an appropriate way to control and check the stability of the result. Although the most problem, it is impossible to know the true confidence interval, bootstrap is asymptotically more accurate than the usual interval obtained using sample variance and assumption of the normality. The bootstrapping is also a convenient method that avoids the cost of repeating the experiment to get other group of sample data. The disadvantages of this bootstrap is the bootstrap depend heavily on the estimator used, and though simple nav use of the bootstrapping will not always yield asymptotically valid result and can lead to inconsistency. The bootstrapping is asymptotically consistent. It does not provide general finite sample guarantee. The result may depend on the representative samples. The bootstrapping can be time consuming, and there are not many available software for bootstrapping, as it is difficult to automate using usual statistical computer package. Now, we have done some literature review to see the trend of the publication of this bootstrapping. So, to see this trend, we assume that the approximately 3% articles published in the PubMed will be using the bootstrap method on biomedical research. So to validate this hypothesis, we assume that the level of significance is 5%, and the P, as I have assumed, it's 3%, and the Q is 97%, and the margin of error we have taken the 5%. So we have estimated a sample size which comes 45. We have taken a total 50 articles, and we selected this article randomly from the last 5 years, and we have taken 10 articles, original article for the last 5 years, 10 from the each year. The search database we have used is the PubMed database. We have selected this database purposely because this database is basically publishing the articles related to the biomedical research. The inclusion criteria was the all kind of original article who are whose full length paper are available in the database. We have excluded all the review articles, SART report, letter to editor, case study, and also for the abstract. Now, if you see the trend of the publication related to the bootstrap, we see that in 2000 it is almost 251, and over the year its trend is increasing. Means the people are becoming aware about these techniques and they are applying this technique in their research papers. Now we compare this in the national versus international. We found that in the international research articles, the trend is increasing in good number, but when we see in the national level, we found that this trend is very less. The type of estimate in PubMed published article used here, the most of the articles which we have selected randomly, 42.1% have used for the comparison purpose, 26% used for the regression. The other we have mentioned 14.9. The risk is for the risk estimation it is 10.5, and time to event it is 4.4, and for the point estimation it is 1.8. The study area, we can see here the most of the articles we found that they are in the either in the public health or the basic sciences. In the medicine, we can see here it is around 20%. For the laboratory, it is 14%. Surgical, it is 4%, and in the radiation, it is only 2%. We have also estimated how many times they have resampled. We found that the 6% has resampled up to 100 times, and 40% is resampled between 101 to 500 times, and 44% is 501 to 1000 times, and 22% is 1001 to 500 times, and 12% is between 5001 to 10,000, and above 10,000 is only 2%. We have also estimated how many sample size they have used. So we found that the 20% the articles, they have the sample size is up to 100. The 32% articles have sample size between 101 to 500, and 22% articles have the sample size between 501 to 1000, and the 10% has 1000 to 500, and above 5000 it was 16%. Now the overall conclusion of this bootstrap method. So bootstrap allow researchers to calculate confidence interval, standard error, or the other statistic, along with measuring accuracy of estimate using the sample itself by resampling over and over again from the original sample. Bootstrap analysis cannot repair a highly biased sample. The larger samples tend to produce better precision and narrower confidence interval. The bootstrap may improve research opportunity by allowing researchers to work with the smaller samples and more accurately measure uncertainty of estimate and inferences. Direct estimation of confidence interval and standard error are limited. Even in statistical software, direct use of bootstrap is limited, and it's require a programming skill. The bootstrap are useful when there are no analytical form or an asymptotic theory to help estimate the distribution of a statistic of interest, where the original sample is too small to use a parametric method to derive the measure of central tendency and dispersion. Bootstrap may be used, especially intended to represent national level population estimates. These are some softwares which we are using the bootstrap techniques. Now these are the references. Thank you.